Let us look at root stratification in cold tundra soil. Roots are typically confined to the warmer and slightly better drained soil layers above the permafrost. In contrast, alpine plants possess roots that penetrate more deeply into the soil for drainage. In contrast, alpine plants possess roots that penetrate more deeply into the soil for drainage is generally much better, and permafrost, if present, is quite deep during the growing season. During much of the summer in northern Alaska, the root tips of a wildleaf polar grass and many similar plants followed within 0.5 to 1.5 centimeter of the retreating frost level in a saturated soil whose temperature were between 0 degree to 1 degree centigrade. Water absorption by roots in frozen ground where part of the water remained in the liquid state because of the high osmotic concentration in the soil as well as in the root. And when we talk about the osmotic values and the Arctic plants, the osmotic values for East Greenland plants are higher in winter than in summer. The drop in osmotic values during the spring is associated with the temperature rise and the utilization of food reserves. Plants covered by winter snow have slightly lower osmotic values than the plants growing in exposed situations. Higher osmotic values of the plants may be due to stronger winds and lower atmospheric pressure when compared with plants at lower altitudes. Stronger winds and lower atmospheric pressure control the water economy of the plants, which is reflected in the higher value of the exposed shrubs than for the rosette with the thick tap roots. Here you can see the pressure difference. The higher osmotic values of the alpine plants may be due to low temperatures. Let us look at the other effects of the temperature. Relatively high summer temperature appears to be the primary restrictive factor limiting the distribution of Arctic and alpine population. At high temperatures, the photosynthetic economy is low, which reduces the carbohydrate reserves. Rates of plant growth in the northern Alaska were correlated with temperatures. The next environmental factor, extrinsic environmental factor, is the wind. So wind speed is greatly reduced near the ground, but in the tundra, the lower stature and the sparse cover of vegetation enable the wind to be more effective than with the taller and more stratified vegetation. Due to this, the wind erodes vegetation mats and cushion in the Arctic. The natural cycle involving wind erosion and frost heaving in the degradation of peat hummocks through frost scars to sorted polygon on which, after flooding, peat accumulation is again initiated. That any community that might be called climax is of short duration. Wind and the plant growth. Wind is effective in reducing leaf temperatures as well as air temperature, thus upsetting the more favorable temperature microclimate of low Arctic and alpine vegetation. This is a negative effect. The potent effect of wind on tundra vegetation is the result of sensitivity of plant growth to wind, and that the sensitivity is due to less to excessive transpiration and more to temperature conditions as they affect net assimilation and shoot growth rates. Transpiration rates for the tundra shrubs are low and directly related to air temperature, vapor pressure deficit, and wind speeds below 6 miles per hour, but inversely proportional to wind speeds above 6 to 8 mph and cloud cover. Transpiration difference were related to morphological structure and leaf anatomy. Cuticular transpiration losses were quite low in xerophytic species but quite high in wet site species. Let us look at snow cover. The snowbank or snow flush vegetation is commonly found in the tundra of mountain areas where winter snow accumulation is large. Drift is favored by strong winds and heavy snowfall. In most low Arctic and alpine tundras, there is a rather specialized flora associated with snowbanks. The microzonation of species and vegetation is largely the result of adaptations to depth and duration of snow cover. The plant must be able to complete at least a vegetative life cycle in a few weeks and even that cannot occur every year. Some species begin growth under as much as 50 to 100 centimeters of snow, whereas other species await the melting of snow before starting to grow. Let us look at the relationship between snow cover and the growth. Development of new shoots, including accumulation of nitrogen under less than 110 centimeters of snow starting in January, is possible for few plants. Some species may remain under snow for 2 or more years, unable to carry on many physiological processes. The presence of relatively large storage of carbohydrate reserves in roots and rhizomes may permit survival that otherwise could not occur in other parts of the world. Plants buried under winter snow do have protection during the critical periods of high wind and low temperature. In summer, the meltwater prevents plants being subjected to soil rot. In general, tundra shrubs are found only where winter snow cover prevails. The shrub height is quite well correlated with mean winter snow depth. Accumulation of dirt on snowbank in the Arctic and its role in building a fine organic soil, as well as possible increase in soil nitrogen.